When the first rays of dawn crept across the surface of the young Earth more than 4 billion years ago, there were no eyes to witness the shimmering oceans of molten rock that rippled beneath a toxic sky. Yet the planet remembered every turbulent second. In the slow churning of magma currents, in the crystalline archives of the earliest minerals, and in the silent stratigraphy of ancient basins, geology began writing its story long before any living creature developed the language to read it. The Earth's crust, still fragile and fractured from its violent birth, cooled in restless pulses, forming continents not as stable foundations, but as wandering rafts drifting across a sea of incandescent silicate. These drifting fragments, precursors to the continents we know today, collided and separated with a ferocity that reshaped the globe countless times, forging mountains higher than any that now break the clouds, and leaving behind scars still visible to geologists who trace the fossilized edges of vanished oceans. Beneath these first continents, minerals such as zircon crystallized from the cooling melt, capturing within their atomic structures the memories of temperatures and pressures now long gone. Those tiny zircon grains, no bigger than a grain of sand, would one day become the oldest known solid materials on the planet, some of them surpassing 4.3 billion years of age, predating even the formation of the Moon's oldest crust. Each one acts like a microscopic time capsule, preserving isotopic clues to the chemical conditions of the Hadean Earth, a world devoid of life, yet already shaping the foundations upon which every future organism would depend. Long before the first oceans fully condensed, volcanic islands rose and crumbled in cycles of creation and destruction, their basaltic surfaces blackening the sky with ash, while rivers of lava poured into primordial seas whose temperatures likely hovered near boiling. As the planet continued to cool, the unstable crust thickened and stabilized in patches, giving rise to the first proto-continents, small buoyant blocks of silica-rich rock called cratons. These ancient cratons, such as the Canadian Shield and the Pilbara Craton in Australia, would survive billions of years of tectonic violence, carrying within them the earliest sedimentary sequences ever deposited. In these rocks, mudstones laid down by shallow water currents whisper of coastlines lost to deep time, while metamorphosed volcanic layers record the explosive tantrums of a restless young world. Through these ancient formations, geologists reconstruct the earliest hints of continental weathering, erosion, and sediment transport, revealing that even before complex life appeared, Earth was already sculpting landscapes with wind, water, and gravity.
At the same time, deep within the mantle, convection currents surged like slow-moving oceans of molten stone. These currents, driven by heat escaping from the core, set the rigid plates of the lithosphere in motion. Though no living creature yet existed to interpret these movements, the Earth had begun the grand tectonic ballet that would one day uplift the Himalayas, fracture Pangaea, and open the Atlantic Ocean. The early tectonic cycle was far more intense than today's. With higher internal heat, plates moved faster. Subduction zones consumed crust more aggressively, and volcanic eruptions were unimaginably larger, releasing colossal plumes of gas that shaped the composition of the atmosphere. The very oxygen that humans would one day depend on was absent then, and the world was enveloped in a heavy cloak of carbon dioxide, nitrogen, methane, and water vapor. As time marched forward, the planet's surface changed in ways that only the rock record can faithfully preserve. Around 3.5 billion years ago, pillow basalts on the ocean floor captured evidence of the first stable oceans, while layered mounds of carbonate, known as stromatolites, chronicled the work of early microbial life. These layered structures, built by simple photosynthetic organisms, became some Earth's earliest biological, geologic formations, intertwining geology and biology so tightly that neither discipline can tell the full story of the planet without the other. Over millions of years, these microbes altered the atmosphere and oceans, precipitating minerals, drawing down carbon dioxide, and gradually releasing oxygen as a byproduct, though the atmosphere would not become truly oxygen-rich until billions of years later. Deep in the crust, chemical reactions between water and mantle rocks created serpentinized minerals, releasing hydrogen and generating chemical gradients that may have powered early metabolic cycles. These interactions, preserved in some of the oldest remaining hydrothermal vent systems, reveal how geology set the stage for life's emergence long before the earliest fossils appeared. Even today, the serpentinized rocks of ancient ocean crust preserve the minerals that record this interaction, their textures frozen snapshots of processes that once fueled the planet's earliest ecosystems. While the microscopic dramas of early life unfolded in the oceans, the continents grew slowly, stitched together by magmatic intrusions and metamorphic belts formed during early collisions. Each collision birthed a mountain range, and each mountain range eroded away grain by grain, delivering sediment to the seas where it would compact into new layers of rock, preserving a rich archive of environmental change. Some of these sediments hold clues to ancient climates, recording glacial periods that swept across the planet even when the sun shone with far less intensity than it does today. Banded iron formations, shimmering stripes of red and gray that stretch for kilometers across ancient landscapes, record the dramatic transformation of Earth's oceans as rising oxygen levels caused dissolved iron to precipitate out, staining entire continental shelves with rust-colored minerals. These formations, found in places like Western Australia and Minnesota, are silent witnesses to the Great Oxygenation Event, a turning point orchestrated by microbial life but written into stone by geologic processes.
As the Proterozoic eon unfolded, vast supercontinents formed and broke apart in relentless cycles. Nuna, Rodinia, and Pannotia rose from the amalgamation of continental fragments, only to tear apart millions of years later. Each rifting event accompanied by volcanic outpourings that blanketed entire regions in basalt. These cycles shaped not only the geography of the planet, but also the climate, as the arrangement of continents influenced ocean currents, atmospheric circulation, and the reflectivity of Earth's surface. Geological evidence of these supercontinent cycles lies in the matching rock types on continents now separated by oceans, in the orientations of ancient mountain belts that span multiple land masses, and in the magnetic signatures preserved in rocks that reveal the latitudinal positions of continents long vanished from their ancient locations. During one of the coldest chapters in Earth's history, the planet may have descended into global glaciation events so severe that even equatorial oceans froze, a hypothesis known as snowball Earth. Dropstones found in tropical sedimentary rocks and striated pavements carved by ancient glaciers suggest that ice once extended to low latitudes, locking the planet into a frigid stillness broken only by the explosive release of volcanic greenhouse gases that eventually melted the ice. These snowball Earth episodes sculpted the geological record with unusual deposits, such as cap carbonates, which formed rapidly in the aftermath of global thawing, marking dramatic shifts in ocean chemistry and climate. In their layers, geologists read stories of planetary resilience, evidence that Earth has survived extremes far beyond anything humans have witnessed. When the Cambrian period dawned around 541 million years ago, a new chapter began, a chapter in which life exploded in diversity and left behind abundant fossils that transformed the geologic record. Trilobites scuttled across the seafloor, leaving behind trails etched in mud that hardened into shale. The shells of brachiopods, the burrows of worms, and the imprints of soft-bodied organisms enriched sedimentary rocks with a biological tapestry that geologists decipher to reconstruct ancient ecosystems. These fossils, combined with sedimentary structures such as ripple marks, cross-bedding, and mud cracks, allow geologists to rebuild snapshots of ancient environments with remarkable precision. Layer by layer, the Cambrian seas laid down pages in Earth's chronicle, each one teeming with clues that illuminate the complexities of evolution and environmental change. Meanwhile, tectonic forces continued their slow, inevitable reshaping of the world. The new continents that rose from the oceans
carried mountain ranges built during collisions between volcanic arcs and continental plates. These orogenic belts, some now deeply eroded, others uplifted anew, record the fierce compressional forces that folded and faulted rocks into complex patterns. In places such as the Appalachian Mountains, geologists can trace multiple cycles of mountain building, each one associated with the assembly of a different supercontinent. The metamorphic rocks hidden at the cores of these ranges bear minerals like garnet, kyanite, and starlite, each one a witness to the immense pressures and temperatures experienced deep within the crust.
The oceans, too, changed dramatically as new marine basins opened and others closed. Subduction zones consumed sea floor, creating volcanic arcs whose eruptions deposited thick layers of ash across continents. Some ash layers, rich in zircons and other minerals suitable for radiometric dating, provide precise timestamps that anchor the geologic timescale. By comparing the ages of rocks across continents, geologists trace how ancient shorelines advanced and retreated as sea levels rose and fell, influenced by both tectonics and global climate patterns. Coral reefs grew along tropical shelves, forming limestone deposits that accumulated over millions of years and now stand as towering cliffs in many parts of the world. As the Paleozoic seas continued to shape the continents with their rhythmic advances and retreats, the crust beneath them underwent slow, relentless transformations driven by the internal heat of the planet. Magma bodies cooled deep underground, forming granites whose interlocking crystals captured the gradual solidification of molten rock in exquisite detail. These granitic plutons, exposed only after millions of years of erosion, would later emerge as the cores of mountain ranges. Their pink feldspars and milky quartz grains shimmering in the sunlight like silent relics of ancient tectonic battles. Each pluton, though motionless now, once pulsed with geothermal energy, feeding volcanic systems that shaped coastlines and altered climates, their eruptions leaving layers of ash that would one day help scientists correlate rock strata across continents separated by thousands of miles. On the sea floor, black smokers belched mineral-rich fluids into the surrounding water, creating chimneys of sulfides that accumulated in towering columns. These hydrothermal vents, driven by the circulation of seawater through the fractured oceanic crust, deposited metals such as copper, zinc, and gold in concentrated zones that modern geologists study both for their scientific significance and their economic potential. Yet in the deep past, these same vents served as havens for life, their chemical gradients powering ecosystems utterly independent of sunlight. The minerals precipitated around these vents form textures that, when preserved in the rock record, allow geologists to identify ancient seafloor hydrothermal systems even in rocks billions of years old. These remnants provide rare glimpses into the environments that fostered
some of life's earliest metabolic innovations. As time progressed toward the late Paleozoic, vast swampy forests spread across equatorial regions, their dense canopies dominated by towering lycopsids, giant horsetails, and seed ferns. The trunks of these plants, falling into oxygen-poor waters, accumulated faster than they could decay. Layer upon layer of organic matter built up, and over millions of years, the immense pressure of overlying sediments compressed the soggy peat into coal seams that now run like black ribbons through the stratigraphy of ancient basins. These seams, sometimes tens of meters thick, record the humid greenhouse climate of the Carboniferous period and the extraordinary productivity of its forests. Within the coal itself, geologists find impressions of delicate plant tissues, spores fossilized in remarkable detail, and even resin canals that once carried sap through long extinct vegetation.
Meanwhile, on the tectonic stage, continents drifted inexorably toward one another. The collisions that followed raised colossal mountain chains such as the Veriscan and Alleghenian origins, whose remnants today lie scattered across Europe and North America. These mountains, once rivaling the Himalayas in scale, were shaped by processes that folded and faulted enormous slabs of crust, pushing rocks kilometers above sea level and burying others deep below where they recrystallized into new forms. The metamorphic gradients preserved in these rocks tell of journeys through the crust, from the shales that transformed into gleaming slates to the limestones that became marbles streaked with veins of calcite. By reading the minerals grown during metamorphism, geologists reconstruct the pressure-temperature paths these rocks experienced, essentially following their underground odysseys through the tectonic furnace. When the final suturing of the continents occurred around 300 million years ago, Earth entered the age of Pangaea, an immense supercontinent whose sheer size influenced climate on a planetary scale. Interiors of Pangaea experienced extreme seasonal variations, with scorching summers and frigid winters, far removed from the moderating influence of the ocean. Desert dunes accumulated in great thicknesses, forming the cross-bedded sandstones that now paint the red rock landscapes of modern deserts in regions like the southwestern United States. These ancient dunes preserve the graceful arcs of their wind-sculpted slopes, each inclined layer a record of the shifting winds that once carried sand across vast, barren expanses. At the edges of Pangaea, long rift valleys began to form as tectonic forces slowly pulled the supercontinent apart. In these rifts, volcanic activities surged, creating flood basalts, whose enormous lava flows spread across the land in sheets hundreds of kilometers wide. Some of these eruptions were so massive that they released enough gas and ash to alter global climates for tens of thousands of years. The basalts themselves cooled into dark, dense rocks that cracked into distinctive columnar joints, geometric patterns that today attract the attention of geologists and visitors alike. These rifting events signaled the beginning of the breakup of Pangaea, a process that would reshape the world's oceans and continents for the next 200 million years. During the Mesozoic, as the Atlantic Ocean opened and new coastlines formed, shallow seaways teemed with life. The shells of countless marine organisms, ammonites with their tightly coiled chambers, bivalves with their ridged exteriors, plankton secreting microscopic calcite plates, accumulated on the seafloor, producing thick sequences of limestone and chalk. These sediments, later uplifted and exposed, revealed detailed portraits of ancient oceans, allowing geologists to trace the chemistry of seawater and fluctuations in sea level with remarkable precision. The famous White Cliffs of southern England, made almost entirely of coccolithophores calcareous remains, represent millions of years of quiet marine deposition, each layer compacted by the weight of those above it, yet still preserving the delicate structures of the organisms that formed it.
On the continents, river systems carved channels through soft sediments, their meandering paths preserved in the rock record by point bar deposits and floodplain muds. These fluvial environments captured the footprints of dinosaurs, whose tracks hardened in mud and later lithified into sandstone slabs that record the motion of creatures long vanished. The arrangement of bones in terrestrial sediments, whether transported by floods or buried in place by sudden events, gives paleontologists and sedimentologists clues about ancient ecosystems and the processes that affected them. In some regions, volcanic ash falls buried entire landscapes, creating Lagerstätten, sites of extraordinary fossil preservation, where even feathers, skin impressions, and delicate plant tissues survived the passage of millions of years. As the Cretaceous period advanced, seafloor spreading rates accelerated, raising global sea levels by increasing the volume of mid-ocean ridges. Epicontinental seas flooded large parts of continents, creating environments where marine and terrestrial sediments intermingled. These seas left behind thick sequences of shale that today hold vast reserves of hydrocarbons generated from the accumulation of organic-rich muds in oxygen-poor waters. The chemistry of these ancient seas is preserved in the ratios of stable isotopes within the sediments, allowing geochemists to reconstruct variations in temperature, salinity, and carbon cycling at exceptional resolution. Meanwhile, the rocks deposited along ancient shorelines reveal the migration of barrier islands, tidal channels, and delta systems influenced by the interplay between sediment supply, sea level, and wave energy. All the while, Earth's internal engine continued to drive tectonic change. Subduction zones beneath the western margins of continents produced volcanic arcs whose eruptions scattered ash across thousands of kilometers. Deep beneath these volcanoes, magmas differentiated, crystallizing minerals that recorded the pressures and temperatures of the mantle wedge. These minerals offer clues to the composition of the mantle and the dynamics of subduction zones, showing how water released from the descending slab lowered the melting point of overlying rock, generating the magmas that fueled explosive eruptions. As mountains built by these arcs rose and eroded, their sediments filled inland basins, creating stratigraphic records that revealed the shifting balance between tectonic uplift and surface erosion. As the Cretaceous world drew closer to its abrupt turning point, a chain of tectonic and volcanic events continued to imprint their signatures deep within the rock record, leaving behind mineralogical clues that future geologists would use to decode ancient planetary rhythms. Along the shifting margins of continents, foreland basins formed as immense mountain belts overloaded the lithosphere, causing it to flex downward under their weight. Into these subsiding basins flowed enormous quantities of sediment eroded from the rising ranges, creating thick successions of conglomerates, sandstones, and shales that built upward in rhythmic cycles linked to climate, tectonics, and sea level fluctuations. Each grain of sand deposited in these basins carried the chemical fingerprint of its source terrain, allowing modern geologists to trace the uplift history and erosion patterns of vanished mountains through the study of detrital zircon grains, which preserve within their crystalline frameworks the ages of the rocks from which they were weathered.
In the deep oceans, subtle variations in temperature and salinity guided the growth of carbonate-secreting organisms whose remains carpeted the seafloor in a continuous rain of microscopic skeletons. These calcareous oozes, accumulating atom by atom, built up into vast sequences of pelagic limestones whose isotopic signatures reflect changes in global carbon cycling, ocean circulation, and atmospheric conditions. The layers deposited during warmer periods showed different mineral compositions and thicknesses than those laid down during cooler intervals, allowing scientists to reconstruct long-term climatic oscillations that influenced ecosystems across the planet. In some places, clay-rich sediments rich in volcanic ash captured traces of extraterrestrial material that settled through Earth's atmosphere, embedding within them rare metals such as iridium that would later help identify the signature of distant cosmic events. When the asteroid struck at the end of the Cretaceous, it unleashed forces so immense that they reshaped the geological record across the entire globe. Shocked quartz grains, their crystalline structures deformed by pressures exceeding those found in Earth's deepest mantle, formed instantly at the moment of impact. These grains, scattered worldwide by atmospheric circulation, settled into a thin but distinct layer that now marks the boundary between the Cretaceous and the Paleogene. In the same layer, spherules of once molten rock, tektites, preserve the moment Earth's crust vaporized and condensed into glassy droplets that rained back down across continents and oceans. Wildfires ignited by the heat pulse left soot deposits in sediments thousands of kilometers from the impact site,
while tsunamis carved chaotic deposits along coastlines, mixing marine and terrestrial sediments in turbulent breccias that captured the violence of the event. Yet, even as life reeled from the catastrophe, geology continued its unbroken cycles. In the Paleogene, the planet's climate shifted dramatically as tectonic events opened new oceanic gateways, altering global circulation patterns. When Antarctica separated fully from Australia and South America, the Antarctic circumpolar current began to flow unimpeded around the continent, isolating it thermally and contributing to the development of ice sheets that would eventually grow to cover the landmass entirely. The sediments deposited along the continental margins of Antarctica record this transition with exquisite clarity. Warm water microfossils give way to cold water species, while dropstones embedded in fine-grained marine muds revealed the presence of icebergs calving from expanding glaciers. Far to the north, the story unfolded differently. The uplift of the Tibetan Plateau, caused by the collision of the Indian subcontinent with Eurasia, dramatically altered atmospheric circulation. The growth of this immense highland intensified the Asian monsoon system, drawing moist air inland and shaping weather patterns that would influence erosion on a continental scale. Rivers draining the rising plateau carved deep gorges and transported staggering volumes of sediment to surrounding basins, forming thick alluvial fans that prograded outward in great aprons. These deposits, interbedded with volcanic ash from distant eruptions, preserve not only the sedimentary record of mountain building, but also the evolutionary history of the animals that inhabited these landscapes, their bones preserved in the sands and silts of ancient floodplains.
As the Neogene progressed, shifting climatic conditions led to the spread of grasslands across many parts of the world. Wind-blown dust, carried from arid regions, settled in thick accumulations known as loess, which compacted over time into fertile soils that now sustain vast agricultural regions. Within loess deposits, geologists find microscopic grains of quartz and feldspar, whose shapes and surface textures reveal the intensity and duration of wind transport. Magnetic minerals within these deposits record subtle changes in Earth's magnetic field, providing a chronicle of geomagnetic reversals and excursions that occurred over hundreds of thousands of years. These magnetic signatures allow geologists to correlate loess sequences across continents, reconstructing global climatic patterns during the ice ages. Meanwhile, the oceans continued to evolve, their chemistry shifting in response to tectonic reorganizations, biological innovations, and fluctuations in sea level. Coral reefs expanded across warm, shallow waters, building massive carbonate platforms whose vertical growth could keep pace with moderate sea level rise. These reefs, now preserved as limestone formations, contain intricate fossil assemblages that document the evolution of marine ecosystems
and the shifting balance between reef-building corals and the organisms that competed with them. In deeper waters, the dissolution of carbonate sediments at the carbonate compensation depth created sharp transitions in sediment type, allowing geologists to map ancient oceanic conditions in 3 dimensions by analyzing core samples extracted from the seafloor. On land, volcanic activity left its own indelible marks. The formation of large igneous provinces, such as the Columbia River basalts, released floods of lava that reshaped landscapes and influenced climate. The basalt flows preserved columnar joints, vestibules filled with secondary minerals like zeolites and agates, and cooling features that reveal the physical properties of the lava at the time of emplacement. Ash from distant eruptions settled into lake basins, where it formed distinct layers that geologists now use as time markers to correlate sedimentary sequences across regions. Some ash layers are so widespread and so well dated that they serve as invaluable tools for reconstructing the chronology of past environments and the organisms that inhabited them. As the Pleistocene ice sheets advanced and retreated in rhythmic cycles driven by orbital variations, they sculpted the continents with a force unmatched by any other erosion process. Glaciers carved U-shaped valleys into mountain ranges, gouging out deep basins that would later fill with lakes. They transported boulders the size of houses for hundreds of kilometers, depositing them as erratic blocks far from their sources. When the ice melted, vast outwash plains formed from the torrents of meltwater that carried finer sediments downstream, building braided river networks that shifted constantly across their gravelly beds. The glacial tills left behind contain unsorted mixtures of clay, silt, sand, and boulders, their chaotic textures recording the grinding, bulldozing movement of the ice. In some regions, the weight of the ice depressed the crust so deeply that even today, thousands of years after the glaciers vanished, the land continues to rebound upward in a slow process known as isostatic adjustment.
As the last of the great Pleistocene ice sheets retreated from the continents, leaving behind braided rivers that sparkled across the newly exposed plains, the Earth entered a new phase in its geological story, one defined by the rapidly changing interplay of climate, hydrology, and the surging pulse of life that recolonized landscapes scrubbed clean by centuries of glacial scouring. In the valleys once filled with ice a kilometer thick, the retreating glaciers left behind kettles that filled with water to become lakes, eskers that wound like sinuous ridges across the land, and moraines that marked their former boundaries like silent monuments to the planet's cold past. The meltwater, released in torrents when glacial dams burst, carved immense channels into bedrock, forming features such as the channeled scablands of North America, whose colossal flood pathways reveal the unimaginable power of catastrophic hydrologic events.
The boulders scattered across these eroded landscapes, some weighing tens of tons, testify to forces that would have seemed supernatural to any human culture witnessing them firsthand. Meanwhile, on coastlines around the world, rising sea levels flooded river valleys, transforming them into estuaries, where sediments accumulated in layered sequences that record the transition from glacial to post-glacial environments. These coastal deposits contain shells from marine organisms whose species distributions shift vertically through the sediment column, marking changes in water salinity, temperature, and depth. By studying these fossils, geologists reconstruct the pace of sea level rise with astonishing precision, correlating these findings with global records of ice volume and atmospheric greenhouse gas concentrations. In regions where the land rebounded faster than the sea level rose, ancient shorelines now sit high above the modern coast, etched into bedrock cliffs as strand lines that form staircases of former beaches ascending inland. These relics, perched far above the waves, map the long-term dance between isostatic uplift and eustatic change. As climates warmed further during the Holocene, rivers stabilized into drainage patterns that persist today, carving channels into floodplains composed of fine silts and clays delivered by seasonal flooding. Meanders developed, swinging across valley floors in sweeping arcs whose abandoned loops, oxbow lakes, dot the landscape like blue teardrops left behind by water's meandering memory. The sediments deposited during these floods record environmental changes on annual to millennial scales, capturing sand from storm surges, mud from quiet waters, and organic remains that offer clues to vegetation shifts and human activity. Paleosoils, ancient soil horizons, formed within these deposits, preserving root traces, clay minerals, and chemical signatures that reveal episodes of drought, fire, and ecological transition. These soils, found in stacked sequences, serve as a diary of landscape evolution, each layer marking a chapter in the dialogue between climate, vegetation, and sedimentation.
In volcanic regions, eruptions during the Holocene sculpted terrains with dramatic suddenness, depositing ash that settled into layers now used as chronological markers across continents. The chemistry of tephra allows geologists to trace a single eruption across thousands of kilometers, synchronizing archaeological and geological records by linking artifacts, fossils, and sediments to specific volcanic events. Lava flows, once incandescent rivers, hardened into basaltic fields whose surfaces cracked into polygonal patterns as they cooled. Within these flows, gas bubbles formed vesicles, later filled with colorful secondary minerals such as calcite, chalcedony, and zeolites, creating miniature mineralogical galleries that reveal the conditions of alteration long after the eruptions faded into memory. Some eruptions emptied magma chambers so rapidly that the overlying rock collapsed,
forming calderas that filled with lakes or were later rejuvenated by renewed volcanic activity, producing nested structures that record cycles of magmatic resurgence. In tectonically active regions, earthquakes reshaped landscapes with abrupt, sometimes catastrophic precision. Fault scarps rose across plains in a single violent moment, offsetting streams and leaving behind displaced terraces that record cumulative strain accumulated over centuries. Liquefaction during strong shaking transformed solid ground into temporary fluid, sinking structures and preserving sand dikes that cut upward through older sediments as evidence of past seismic unrest. By dating organic material within these disturbed layers, paleoseismologists build timelines of earthquake recurrence that extend far beyond historical records, revealing patterns that help modern societies prepare for future events. In subduction zones, the sudden release of tectonic stress generated tsunamis whose deposits blanketed coastal lowlands with anomalous sands, carrying marine shells and waterlogged debris far inland. These tsunami deposits, preserved between peat layers, tell of cycles of megathrust earthquakes that recur with sobering regularity. As the continents continued their slow drift across the globe, plate movements opened rift valleys in some regions while compressing crust in others. In the East African Rift, lakes formed within elongated depressions where the crust thinned and subsided, capturing sediments that preserve records of ancient climate fluctuations driven by monsoon intensity and orbital variability. These sediments, rich in diatoms and other microfossils, show transitions from deep, freshwater lakes to shallow, saline basins, each phase corresponding to shifts in precipitation patterns and hydrologic balance. Rift volcanism produced basaltic fields, tuff cones, and hydrothermal systems that altered minerals in surrounding rocks, creating zones of intense metamorphism where hot fluids circulated through fractures, depositing copper, gold, and other metals that accumulated in economically significant concentrations. The tectonic processes shaping this region today mirror those that operated during the formation of ancient ocean basins, offering a glimpse into the early stages of continental breakup.
Elsewhere, mountain ranges continued to rise as tectonic forces pushed crustal blocks upward. The Andes, formed by subduction along South America's western margin, developed complex structures where volcanic arcs, fold-thrust belts, and foreland basins interacted in dynamic equilibrium. As these mountains grew, erosion removed vast amounts of material, delivering sediment to the Amazon basin, where it accumulated in thick sequences that record the evolving drainage patterns of one of the world's largest river systems. Deep within the Andes, metamorphic processes produced high-grade rocks such as migmatites and granulites, their intermingled light and dark bands revealing partial melting and recrystallization under extreme conditions. These rocks, exhumed by millions of years of uplift and erosion, expose the deep roots of orogenic systems and allow geologists to reconstruct the pressures and temperatures
that prevailed tens of kilometers below Earth's surface. On ocean floors, slow but persistent processes left their own intricate signatures. Pelagic clay settled from the water column at rates sometimes measured in millimeters per millennium, forming deposits so fine and uniform that they captured changes in ocean circulation and atmospheric dust flux with remarkable fidelity. At mid-ocean ridges, basaltic lavas erupted continuously, creating new oceanic crust that spread outward like conveyor belts, carrying magnetic stripes that record the history of geomagnetic reversals. The symmetry of these stripes across ridge axes provided the decisive evidence for seafloor spreading, a key component of plate tectonic theory. Hydrothermal alteration along these ridges produced distinctive mineral assemblages, chlorite, epidote, and serpentine, that reveal the temperatures and fluid compositions circulating through the crust. Eventually, much of this oceanic crust would be forced back into the mantle at subduction zones, carrying water and sediments that influence mantle melting and the chemistry of arc magmas. Meanwhile, deserts expanded and contracted across continents as climate oscillated, depositing thick layers of sand that formed dunes whose cross-bedded structures preserved the shifting wind regimes that sculpted them. Some desert landscapes contain yardangs, streamlined ridges carved by wind erosion, whose orientations revealed the persistence and directionality of ancient wind patterns. Evaporite deposits developed in arid basins where lakes dried up repeatedly, leaving behind layers of halite, gypsum, and other minerals, whose crystal shapes and fluid inclusions trap microscopic samples of ancient waters. These evaporites, sometimes hundreds of meters thick, hold geochemical clues to the climate, hydrology, and tectonic setting of their basins of origin, allowing geologists to reconstruct environmental histories that stretch back millions of years.
In regions where deserts transitioned into semi-arid steppe, the interplay of wind, water, and sparse vegetation created alluvial fans that spread outward from mountain fronts like vast stony deltas built not by rivers, but by sudden, sediment-laden flash floods. Each debris flow deposited angular fragments of rock within poorly sorted matrices of sand and silt, forming conglomerates whose classed compositions reveal the lithologies exposed in upland source terrains. Over time, successive pulses of sediment stacked into thick aprons along basin margins, and as tectonic subsidence deepened these basins, the fans advanced and retreated in response to climatic fluctuations. Within the layers of these fans, soil horizons developed intermittently during periods of landscape stability, capturing chemical signatures of vegetation shifts and moisture availability that allow modern geologists to reconstruct paleo-environments with exceptional nuance. Farther toward coastal plains, deltas built outward into seas and estuaries, where river systems delivered enormous quantities of sediment derived from erosion deep within continental interiors. These deltas, shaped by the competing influences of waves, tides, and river discharge, formed complex networks of distributary channels, crevasse splays, and interdistributary bays. In their sediments, geologists find plant fragments, charcoal from ancient fires, shells from brackish water organisms, and layered sand bodies that reflect sudden channel shifts known as evulsions. The stacking patterns of these sands and muds record the rhythms of sea level change, seasonal flooding, and tectonic subsidence, offering a window into how coastlines migrated landward or seaward over millennia. In some regions, buried deltaic sands later became reservoirs for hydrocarbons generated from the organic-rich muds that accumulated around them, forming the basis for some of the world's most significant energy resources. Offshore, the continental shelves preserved their own geological archives. During glacial periods, when sea levels dropped by more than 100 meters, rivers extended their courses across exposed shelves, carving channels that now lie submerged beneath modern oceans. These paleochannels, infilled by post-glacial sediments, reveal the pathways of ancient river systems whose deltas shifted seaward during times of low sea level. When the ice melted and sea levels rose, wave action reworked shoreline sands into barrier islands and submarine dunes whose preserved orientations reflect dominant wave and current directions. Beneath these modern sediments, older deposits record cycles of transgression and regression, driven not only by glacial-interglacial rhythms, but also by subsidence patterns tied to salt tectonics, sediment loading, and deeper crustal processes. As one moves deeper still into the realm of the continental slope, turbidity currents shaped the seafloor with dramatic force. These underwater avalanches of sediment swept downslope through submarine canyons, depositing graded beds of sand, silt, and clay that formed characteristic sequences known as bauma structures. Each graded layer captures a single event, a moment when sediment-laden water rushed downslope before slowly settling into distinct textural divisions. Over time, thick accumulations of these turbidites stacked into submarine fans that extended for hundreds of kilometers, forming some of the largest sedimentary bodies on the planet. Their structures, preserved in exquisite detail, allowed geologists to reconstruct the dynamics of deep-water sediment transport and the tectonic settings that create the steep gradients necessary for such flows.
In the quiet depths of the abyssal plains, where sunlight never penetrates and the water remains near freezing, pelagic sediments continued to settle with patient uniformity. The slow accumulation of red clays, composed of weathering products carried by atmospheric dust and volcanic ash, formed deposits so ancient that any bioturbation by deep-sea organisms barely disturbed their stratified layers. Manganese nodules grew on the seafloor surface, through the accretion of metal oxides around small nuclei, shark teeth, shell fragments, or even tiny rock particles, forming rounded or cauliflower-like structures that contain valuable metals such as cobalt and nickel. These nodules, which grow only millimeters per million years, are among the slowest forming geological materials on Earth, their surfaces recording changes in ocean chemistry across vast stretches of time. Beneath the seafloor, in the dark realm of the upper oceanic crust, hydrothermal systems circulated seawater through networks of fractures and pillow basalts. The water, driven by heat from underlying magma bodies, altered the mineralogy of the crust, producing greenstones rich in chlorite and epidote. In deeper sections, the transition to sheeted dike complexes revealed the conduits through which magma once rose to feed seafloor eruptions. Still deeper, gabbros formed as slow-cooling intrusions, their coarse crystals of plagioclase and pyroxene, recording the crystallization history of oceanic crust forming at mid-ocean ridges. Modern drilling expeditions extracting cores from these regions have provided unprecedented insight into the structure of the oceanic lithosphere, confirming models of crustal accretion developed through seismology and field studies of ophiolites, pieces of oceanic crust thrust onto land by tectonic forces. Meanwhile, in continental interiors far from active margins, ancient cratons maintained their quiet stability. Their roots extended deep into the mantle, forming thick keels of lithosphere that protected them from the intense recycling processes that consumed younger crust at subduction zones. Within these cratonic interiors, some of the oldest rocks on Earth survived virtually unaltered, including Archean greenstone belts, composed of metamorphosed volcanic and sedimentary rocks. These belts preserve rare evidence of early oceanic crust, volcanic arcs, and sedimentary processes that operated more than 3 billion years ago. Interspersed with them are tonellite, trongemite, and granodiorite complexes, intrusive bodies that reveal the high-pressure melting of hydrated mafic crust deep within early subduction settings. These ancient terrains hold the chemical clues to the evolving composition of Earth's early mantle, crust, and atmosphere, offering rare glimpses into a world whose conditions differ markedly from those of the present. Diamonds, formed under crushing pressures more than 150 kilometers beneath the surface, rose toward the crust in explosive kimberlite eruptions that tapped the deep mantle. The diamonds themselves, carried upward in xenoliths of peridotite and eclogite, contain microscopic inclusions that record conditions of extreme pressure and temperature. Some diamond inclusions preserve minerals stable only in the lower mantle, making them unique natural samples of regions otherwise inaccessible to direct observation. Kimberlite pipes, now deeply eroded, dot the ancient cratons and stand as rare pathways by which material from Earth's interior journeyed swiftly to the surface, providing mineralogists with unparalleled access to the deep Earth.
Within mountain belts, metamorphic rocks reveal long histories of burial, heating, deformation, and exhumation. Schists shimmer with mica that aligned under directed pressure, their foliation tracing the shear zones through which the rocks were transported during tectonic collisions. Gneisses display striking banding that represents the segregation of light and dark minerals under high-grade metamorphic conditions. In the roots of ancient origins, eclogites preserve garnet and omphacite assemblages, indicative of subduction to depths exceeding 80 kilometers. These rocks, now found on the surface due to uplift and erosion, provide geodynamicists with critical constraints on the behavior of tectonic plates as they dive into the mantle, a process whose early evolution remains one of the most intriguing mysteries in Earth science. In volcanic arcs above subduction zones, stratovolcanoes built layer upon layer of andesite and dacite, their flanks composed of interleaved lava flows, pyroclastic deposits, and lahars. Some eruptions deposited ignimbrites, vast, densely welded textures formed by the collapse of pyroclastic density currents that raced across landscapes at hurricane speeds. These deposits preserve vesicle textures, welding fabrics, and mineral zoning patterns that allow volcanologists to reconstruct eruption dynamics and magma chamber evolution. Caldera eruptions, among the most explosive events known, left behind depressions tens of kilometers across, sometimes partially filled by resurgent domes, indicating renewed magmatic intrusions after the main eruption subsided. The geochemical diversity of arc magmas, influenced by slab-derived fluids, sediment melts, and mantle wedge dynamics, provides deep insight into the recycling of crustal materials within Earth's interior.